Welcome everybody to the second part of the lecture related to chapter 3. Let's go to slide number 32 and talk a little bit about the division of national income. So the economic profit is equal to the output minus what goes to the factor labor minus what goes to the factor capital. When we put these two terms on the other hand side of the equation, they pop up with positive signs. And then we can put like y on the left hand side and the three terms on the right hand side. In the market structure of perfect competition, in the long run equilibrium, the economic profit is equal to 0. And then it becomes clear that the whole output is divided between the owners of the factor labor and the owners of the factor capital. A follow-up question is how much goes to the owners of the factor labor and how much goes to the owners of the factor capital. Let's have a look at some empirical evidence. Like here we can see the labor's share of total income. It is related to the US and we have here like a line diagram over time. And one can see that this ratio is pretty stable over time. It is about 70% goes to the owners of the factor labor. Why is it so constant? This was also a question addressed by the two economists Cobb and Douglas, and they invented the so-called Cobb-Douglas production function, which will be in the focus of the next few minutes. So here we can see this Cobb-Douglas production function. A is the technology parameter, K is the capital units, and L are the labor units. The Cobb-Douglas function has the following characteristics. The marginal productivity of labor. There we have to differentiate the production function with respect to L. When we do that, like we have to write the exponent in front of the expression and multiply through by the exponent. And then we have to reduce the exponent by 1 unit. Let's do that. We have to write the exponent in front of the expression and then multiply through, reduce the exponent by 1 unit. Then we get to this relationship here because there is a positive one and there is a negative one. So it's L to the power of minus alpha. We can also do the same with respect to capital. So we differentiate the production function with respect to capital to get the marginal productivity of capital. So once more, we have to take the exponent, write it in front of the expression and multiply through. And we have to reduce this exponent by 1 unit. So the exponent and then multiply through, reduce the exponent by 1 unit. In the following, we will concentrate on the marginal productivity of labor because of the fact that in this graph we had the labor's share of total income, and we want to explain why the labor's share of total income is constant. So we'll focus on the marginal productivity of labor. Marginal productivity of labor was given by this equation. And now we will multiply through the last part by 1. L over L is equal to 1. So we are multiplying through the right-hand side by 1. Now we can sort the terms a little bit differently. We can write the product on the numerator of this fraction. In the denominator, we have L. Now it is a case that we can combine L and L to the power of minus alpha, and we get L to the power of 1 minus alpha. And now when you look at the numerator is nothing else than the output y, because the numerator is equal to the production function. So we can also write that the marginal productivity of labor is equal to 1 minus alpha times y over L. When we put L to the other side of the equation, we can see here that it is the case that the labor share of output is equal to 1 minus alpha. And as long as alpha is constant, it will be the case that the labor share is constant. When we perform the same procedure for capital, then it is the case that we get to equation 38. Marginal productivity of capital times capital is equal to alpha times the output level y. Alpha because the exponent attached to capital is equal to alpha. When we now divide 37 by 38, we get to this relationship here. Marginal productivity of labor times labor divided by marginal productivity of capital times capital is equal to 1 minus alpha times output divided by alpha times output. Now we can cancel the output variable and we get to this relationship here, and on the following slide we are going to interpret this equation number 40. It is the case that the ratio of labor income to capital income is constant. It is constant as long as the production function is constant. So the factor shares depend only on the parameter alpha and not on the amounts of capital, not on the amounts of labor, and it also does not depend on the state of the technology, which is measured by this variable a. The variable a does not pop up in this fraction. Until now, we talked about this relationship in a theoretical setting. Let's have a look at our numerical example. In our numerical example, we work with the following production function. F is equal to k to the power of 0.5 times L to the power of 0.5. So alpha was equal to 0.5. When we insert this value in this expression, it is clear that the numerator and the denominator both take the value of 0.5, so that the ratio is equal to 1. This implies that 50% of the output goes to the factor labor and 50% of the output goes to the factor capital. Let's check whether this is indeed the case. Is it really the case that the amount of output which goes to the owners of the factor labor is equal to the amount of output which goes to the factor capital? Let's check. We are assuming the following. Our economy has 25 units of labor and 100 units of capital. We have to answer the following question. What is the equilibrium value of the real wage, like the marginal productivity of labor? Then we have to answer the question, what is the equilibrium value of the real rent, or like the marginal productivity of capital? And we also need to know how large is the output and how is it split up. So in the first step, I would like to use the following graph, which is already familiar to you, where we plotted the marginal productivity of labor when capital is equal to 100. In this example, we assumed that the economy is endowed with 25 labor units. So we have to find the value of 25 here on the horizontal axis, which is here. And when we insert the amount of labor in this marginal productivity of labor relationship, then we get the information that the equilibrium marginal productivity of labor is equal to 1. So the wage rate, the real wage in equilibrium, is equal to 1. Therefore, we also know that 1 times 25, like 25 units, will go to the owners of the factor labor. Let's have a look at part B. Let's have a look at the marginal productivity of capital. We have to compute the marginal productivity of capital in the following way, that we differentiate the production function with respect to k. We get to this relationship here, and then we can put k in the denominator because here k goes to the exponent of minus 0.5. Therefore, in the denominator of this fraction. So now we are able to derive the function of the marginal productivity of capital. We have to set in L equal to 25, and then we are able to create this graph. So this graph represents the marginal productivity of capital in case that L is equal to 25. Now we have to find the value k is equal to 100, which is given here. So the marginal productivity of capital in equilibrium is equal to 0.25, so that the real rent will be equal to 0.25 in equilibrium. 0.25 times 100 is equal to 25. So 25 units of the output go to the factor capital. On the next slide, we focus on part C. How large is the output and how is it split up? The production function was given by y is equal to k to the power of 0.5 times L to the power of 0.5. The economy is endowed with 100 units of capital and 25 units of labor. So when we take the square root of 100 and the square root of 25, we get 10 times 5, which is equal to 50. So the output is equal to 50 units. And how is it split up? We talked about that already. The marginal productivity of labor, which is equal to the real wage, is equal to 1. 1 times 25 labor units, so 25 units go to the factor labor. Marginal productivity of capital is equal to the real rent. The real rent in equilibrium is 0.25. 0.25 times 100 is equal to 25. So 25 units go to the factor labor, 25 units to the factor capital. So the output is split 50%, 50% among the owners of the factor labor and the owners of the factor capital. That the ratio is equal to 1 was already obvious when we looked at this relationship here, like on slide number 39. On slide number 39, we derived the result that this ratio is equal to 1 minus alpha divided by alpha. And when we plugged in the values for alpha in our numerical example, it was clear that this ratio has to be equal to 1. We just used this graphical approach in order to determine the marginal productivity of labor and also the marginal productivity of capital in equilibrium. And then we were able to confirm that this is indeed the case, that the output of 50 is split up in the following way: 25 to the factor labor and 25 to the factor capital. We started this subchapter by looking at the following graph, where we can see the labor's share of total income over time, which is pretty constant. So it seems to be the case that the production function is pretty constant over time. In the textbook, they really zoom in and they observe that in the last few years, there is a small tendency that the labor's share of total income decreases. And in case that you are interested in this discussion, please have a look at the textbook. They talk about why the labor share of income is decreasing a little bit in the last few years. But let's start a new subchapter. Let's talk about the determinants of the demand for goods. So we start by once more looking at the composition of GDP, where we have on the right-hand side the different components like consumption of the private households, investment of the companies, government spending, and net exports. But here in this chapter, we are looking at a closed economy so that exports are equal to 0, imports are equal to 0, and net exports are also equal to 0. Therefore, we only have to focus on these three components, C, I, and G. Let's have a look at the consumption function. Here you can see the figure, like consumption is a function of disposable income. Disposable income is defined as y minus t, so y can be interpreted as the gross income, then the household has to pay taxes, so that y minus t is a net income, which is labeled as disposable income. This curve does not start in the origin. That's very important. It starts like here. The curve does not go through the origin. And then the slope of this curve is equal to the marginal propensity to consume. So the slope is smaller than 1. When you go one step to the right, the curve goes not one step upwards, but the marginal propensity to consume is smaller than 1. What does this imply? In economic terms, it can be interpreted in the following way. In case that disposable income is up by €1, consumption increases only by the marginal propensity to consume. Let's assume that marginal propensity to consume is equal to 0.75. Then, when disposable income increases by €1, consumption is only up by 75 cents. 25 cents are saved by the private household. So therefore, the marginal propensity to consume is very important to find out how is the disposable income split up into consumption on the one hand side and into savings on the other hand side. So marginal propensity to consume, very important in order to answer the question, how much of the income is consumed and how much of the income is saved. So let's have a look at the formulas. Consumption is a function of disposable income, and we can create one explicit consumption function, which is in line with the graph on the previous slide. Consumption depends, of course, on the disposable income, and C1 can be interpreted as the marginal propensity to consume, MPC. The parameter C1 has the following characteristics: that it is smaller than 1 but larger than 0. So C1 is between 0 and 1. Previously, we assumed that C1 is equal to 0.75. Then there's here the autonomous component of consumption. The autonomous component of consumption represents this distance here. And the autonomous component of consumption collects all factors which also affect consumption but are not modeled explicitly. For example, we could assume that not only income but also the wealth of a person affects consumption, so C0 can represent the wealth of a person. C0 can also be interpreted as like the consumer confidence. In case that a lot of people become unemployed in a recession, it might be the case that the autonomous component of consumption decreases because consumer confidence deteriorates. So C0 can be interpreted in a lot of different ways. So let's have a look at the equations. The investment function depends on the real interest rate. There is one numerical example in one of the assignment questions in the textbook, page 77. So I is equal to 1,200 minus 100 times R. We want to model this investment function in the same way, so that we have one autonomous component, the autonomous component of investment, and then B2 is the interest rate reactivity of investment. It indicates by how much investment decreases in case that the interest rate increases by 1 unit. In case that the interest rate increases by 1 unit, then investment will decrease by 100 units. So B2 indicates by how much investment reacts in case that the real interest rate changes. That's all with respect to this investment function, but we have to clarify what is a real interest rate. So I would like to come up with the following numerical example to highlight the difference between the real interest rate and the nominal interest rate. Let's assume that you have xt is equal to 100 euros. The nominal interest rate, which you get in the financial market, is equal to 10%, and the price of a chocolate bar in period t is equal to 1 euro per chocolate bar. The big question is, how many chocolate bars can you afford in the beginning? When you divide the 100 euros by the price of a chocolate bars, it is obvious that you can afford 100 bars of chocolate. 1 year later, let's do a scenario analysis. And in scenario A, there is no inflation and the good price is constant. The price of a chocolate bar in period t plus 1 is equal to 1 euro per bar of chocolate. The financial wealth increased from xt is equal to 100 to xt plus 1 is equal to 110 euros due to the interest payment. How many bars of chocolate can you afford now in period t plus 1? 110, the financial wealth, divided by the price of a chocolate bar is equal to 110. So the amount of chocolate bars increased from 100 to 110, so by 10%, so that in real terms, you also gained 10%. In scenario B, the inflation rate is equal to 10%. The price of a chocolate bar in period t plus 1 is therefore 1.10 euros. How many chocolate bars can you buy in period t plus 1? Financial wealth, 110 euros divided by the new chocolate price of 1.1. So the amount of chocolate bars is equal to 100. So in t, you can buy 100 bars of chocolate. In t plus 1, you can also buy 100 bars of chocolate. So the amount of chocolate you can afford is constant, and therefore the real interest rate is equal to 0. Last scenario, scenario C. The inflation rate is 5%. The chocolate price increases to the level of 105. The amount of chocolate you can afford is equal to 105. So the amount of chocolate increased by 5 units. The real interest rate is equal to 5%. So the relationship between the nominal and the real interest rate is as follows. The real interest rate is equal to the nominal interest rate of I minus the inflation rate. This is an important relationship. It's not focused in the textbook, therefore I came up with this additional information. Why was this important? It was important because the investment function depends on the real interest rate, and the real interest rate was not defined so far. Where do we stand? Like, we wanted to talk about this relationship here, the composition of GDP, and we talked already about consumption, investment, but we did not talk about government spending. Let's do so. That's very brief. The government decides European government spending, and the government also decides European taxes. So government spending and taxes are some exogenous variables. Now that we have defined the composition of GDP and how the different functions looks like, it is time to make some very important remarks. The setting of the model. So the model we are now looking at can be classified as a classical model. The interest rate adjusts, and this brings supply and demand in an equilibrium. So the interest rate is the adjusting factor. And we have two ways of thinking. So we could think about that the interest rate affects demand for goods and services, not supply. This is the one way of thinking. Supply is not affected because of the fact that supply is given by the amount of capital and labor units and our production function, so supply is fixed. The other way of thinking is that the interest rate affects the demand and maybe also the supply of loanable funds. So let's combine demand and supply at the goods market. So we can now insert the information we have. We can insert our consumption function. We can insert our information about the investment function. And we can also insert the information that government expenditure is exogenous. The supply side is given by the amount of capital, the amount of labor, and the production function, so that also Y has a bar. The supply of goods is a constant as long as capital and labor is constant and the production function. So supply is given by these three ingredients: capital, labor, and production function. So we also put a bar above Y. Hence, when supply is equal to demand, we get the following relationship here: supply on the left-hand side and demand on the right-hand side. And when you look at equation number 58, then it is the case that the interest rate is the only variable not already determined in the last equation. And the interest rate is the endogenous variable here, and the interest rate will adjust and bring supply and demand towards an equilibrium. The remaining question is, how does the interest rate adjust? Why does the interest rate adjust? And the best way to understand and give an answer to this question is to consider the financial markets in this story. Let's do so and talk about the financial markets. Let's talk about saving and investment. Once more, we'll start from the composition of GDP equation. We subtract C and we subtract G, so we put C and G on the other hand side of the equation. Now we are getting to equation 60. C and G are on the left hand side, and in the next step we are subtracting T and we are adding T, but only on the left hand side of this equation. So this of course is allowed when we add T, and when we subtract T, more or less we are adding a zero here on the left hand side of this equation. But this step is important in order to sort the elements a little bit differently. So we have here on the left hand side a negative T and also a positive T. Now we can have a look at these terms like Y minus T minus C can be interpreted as private saving. Y is a gross income. The private household has to pay taxes of T, and then the private household is going shopping, so that Y minus T minus C is private savings. Public saving is T minus G. So the left-hand side of this equation 61 can be interpreted as national savings. National savings is equal to private saving plus public saving. So we can insert national saving as on the left-hand side of this equation. And here it is also once more very important to see that the taxes are exogenous, government spending is exogenous, Y is exogenous, and also consumption is exogenous, so that also S is exogenous in this situation, so that we put a bar above S. Now we can come up and create a graph where we have savings and investment in one graph. So savings, this is like the vertical line, and investment, this is the function you're already familiar with because of the fact that we work in the same diagram where we have the real interest rate on the vertical axis and the level of investment on the horizontal axis. So now it is possible to determine the equilibrium level of the interest rate. It is where saving and investment intersect. What happens if we are not in an equilibrium? When we are not in an equilibrium, for example here, when the interest rate is too high, it is the case that investment will be lower compared to saving. The supply of funds at the financial markets is higher than the demand for funds, and therefore it will be the case that the interest rate will adjust, the interest rate will decrease, and therefore the quantity invested will increase. We can also use this diagram in order to discuss some shocks. What happens if government spending increases? We have to find out whether government spending is included in this relationship or in that relationship. Is government spending included in savings or is it included in investment? And in which direction does the one or the other curve shift? Let's once more have a look at equation number 61. Government spending is included in the national savings. So the saving curve will shift. When the government increases government spending, it will be the case that public saving decreases, and when public saving decreases, also national saving decreases. This implies that here the saving curve will shift to the left, and we get a new equilibrium here. The interest rate increases, and it will be the case that investment also decreases. This increase in the interest rate leads to a decrease of investment, and this has a special term, a special label. We call it that an increase in government spending crowds out private investment. Thank you very much for also attending the second part of the lecture. Have a nice day. Bye-bye.